So, good afternoon, everybody. It's a pleasure to start this afternoon session. The first speaker of the session is Kurkcuoglu, Seckin, if I pronounce it well. And the title of his talk is Chaos in Matrix Gauge Theories with Massive Deformations. Please proceed.
All right, thank you very much for the introduction, and I'd like to thank the organizers for inviting me to give a talk here, and it's a pleasure to be presenting a talk here. I'm going to be talking about some recent work that I have been pursuing with my students. So here, let's see how. Here is the outline of my talk. I will start with some motivations and background, and I will introduce a Yang-Mills matrix model and I will discuss some preliminaries, and I will show you how the chaotic dynamics emerges from this model. And if time permits, I will also discuss some recent results on mass deformed ABJM model and the chaotic dynamics emerging from that, and I will end up with some conclusions. So here are some motivations for this work that we have been pursuing. So it's well known, in fact, that in the BFSS and BMN matrix models and related matrix models, there is chaotic dynamics. And we would like to further explore this at the classical level and to make contact with some recent developments. So as many of you will know, these matrix models describe coincident D0 brains, and they have a gravity dual, which is usually called the black brane solution, which is obtained in the large and low temperature limit. So this actually corresponds to the limit where the effective 't Hooft coupling is large. And here lambda is the 't Hooft coupling, which is G square, and G being the Yang-Mills coupling. And there are some recent works which indicate that even not in the low temperature, but in the large and high temperature limit, there is numerical evidence for properties like the black holes have, which are called like fast scrambling. And although this is not the limit in which the gravity dual picture is valid, so therefore we would like to see how the classical dynamics can further be used to understand the chaotic dynamics emerging from these models. Well, the classical dynamics gives a good approximation at the high temperature limit. And there are also some recent results on the BFSS model which tells us how the largest Lyapunov exponent depends on the temperature. This is a result that which shows that the largest Lyapunov exponent actually scales like the 1/4th power of the temperature. This is a result by Gurari and collaborators, and this is actually parametrically smaller than the MSS bound at sufficiently high temperatures, but it violates it at some critical temperature, which can be given as 0.015 here. And I will probably, toward the end of my talk, I will also remark upon some recent developments which which extends these discussions to the quantum level. But let me proceed further. And this is, in fact, the appearance of chaos in Yang-Mills matrix models is not new. It has been known from early 80s due to the work of Matignon and collaborators and due to the Savadi and collaborators. And there were also early works on BFSS model by Arafeva et al. From 1990s. And also Asano et al. Has investigated the chaotic dynamics emerging from BMN models at small matrix sizes using fuzzy spheres at the angular momentum level 1/2 and 1 with some collective time dependence. So, in order to have some non-trivial dynamics of D0 brains and leading to chaos, this requires in the matrix models non-commuting matrices. So fuzzy spheres, which are described by matrices with certain non-vanishing commutation properties, could serve as good candidates for background geometries to probe chaotic dynamics behavior in such matrix models. So, and it's already also known that in the BMN model, fuzzy two-sphere appears as a vacuum solution, whereas the in a certain 5-matrix model, fuzzy four-sphere appears to be so. So just with these backgrounds and data, we prefer a setting in which we'll work in the large N limit where the 't-Hooft coupling is held fixed. And we would like to consider matrix models in which both the fuzzy two-sphere and four-sphere appear in a certain ansatz configuration, which we would like to use in such matrix models. So let me now move on to this particular matrix model that we are going to be interested in. So this is a bosonic matrix model, XR Hermitian matrices. And there are two massive deformation terms here. One of them is related to the first 5 matrices, whereas the other one is related to the other 3. And the 9th matrix in this matrix model will be set equal to 0 as we will move on. There is a single gauge field AT, which transforms in the usual manner. And this matrix model has an SUN gauge symmetry, whereas the global symmetry of the BFSS model, if there were no massive deformations, this would have been the bosonic part of the BFSS model. But with the massive deformations, the global symmetry is broken in this manner. And we have already written this action in the 't-Hooft limit with the 't-Hooft coupling set to unity. And in the A equals to 0 gauge, we can obtain the equations of motion for these matrices, which are subject to the Gauss law constraint, which is given here, where there's a sum over the index I. And if we look at some particular solutions of these equations of motion, you can recall that if we set, say, the xi equal to 0, I being 6, 7, and 8, there will be just the equation in the first line, and that will be solved by fuzzy 4 spheres with mu1 square being a constant minus 16. These fuzzy 4 spheres will be given by these n by n matrices, where n can take on these values with small n running from 1 to 3 integers. And there's also another set of solutions, which are the fuzzy 2 spheres coming from the second equation if we set the other to 0, other matrices. So these just give us some further clues on what are the possible solutions that can be obtained from these matrix models. So we would like to consider now an ansatz configuration in which we take, say, these YA are representing the fuzzy 4-sphere matrices, whereas the ZI are representing the fuzzy 2-sphere matrices, and R and Y are some real functions of time. So we, of course, pick fuzzy 2-sphere matrices at matching matrix sizes with the fuzzy 4 spheres. Although, well, in this matrix model, there's a trace, of course, and you see, for the fuzzy 2 spheres, it will be rather straightforward to compute all such traces analytically, but for the fuzzy 4-sphere matrices, that's quite a difficult task. So we resort to numerical methods to generate the fuzzy 4-sphere matrices at several different matrix levels, running from n from 1 to 6. And then we can exactly compute the traces by using MATLAB or Mathematica. So this leads to some effective actions. And I have written here a family of Hamiltonians that we obtain in this manner. And here you see that the potential is given in this form, where there is a quartic term which is coming like r squared y squared. This is an indication that the model will actually have chaotic dynamics. And here the coefficients C are obtained from computing the traces at different matrix levels. So, and the results for n equals to 7 are actually obtained by extrapolating a rational function fit. So just to see how this goes on further. But in order to investigate the chaotic dynamics, we first look at the fixed points of these Hamiltonians. And so these are given by the solutions of the set of equations, which are, so there are the dynamical degrees of freedom Ry and their conjugate momenta, and the set of the fixed points in the phase space are given by solving these equations. And for n larger than 1, these fixed points are given by the points below, where the h1 and h2 values are written down here in this table. And we have also noted the fixed point energies for these fixed points, and for the fixed point energies of these fixed points, these are given in the following table. And the same table also gives us the minimum values of the potential at several different values of n, from which it is also seen that the fixed point energies at EF are much higher than the minimum of the potential at these different values of n. So why this is useful? Well, in order to see the use of the fixed points, we have to continue the analysis a little bit further, and we would like to look at the stability around these, linear stability around these fixed points. And that can be actually analyzed by looking at the Jacobian matrix, this J alpha beta, which I have written here, and I have defined the phase space coordinates by this generic notation G1 up to G4, corresponding to Ry and the conjugate momenta. Where it is known that for stable fixed points, all the eigenvalues of J alpha should be negative, whereas for the unstable fixed points are characterized by the presence of one or more positive eigenvalues for this Jacobian matrix. And if all the eigenvalues are purely imaginary, that will be a borderline case, which will require a higher order analysis, which we will not go into. And well, it turns out that the fixed points given by this 0 and also given by these numbers h1 and h2n are all unstable fixed points. And there are some borderline cases. And but it turns out that the energy of these fixed points given by these numbers h1, h2 are less than the fixed point energy of this point, which are all given by zeros. And we expect that the chaotic dynamics will start around the energies, just at and around the energies of these fixed points. And from the time series analysis of the Lyapunov exponents, as well as the by obtaining the Poincare sections around these energies, we have confirmed that the chaotic dynamics starts to emerge in these models at and around these fixed point energies. So that is one of the first findings in our work. I will not show you the plots in order to save some time. Then I will move on to something more interesting, and we would like to look at the energy dependence of these Lyapunov exponents. Or more precisely, we would like to understand how the Lyapunov exponents, which since this is a 4-dimensional phase space in the reduced model, there will be just a single positive Lyapunov exponent, and we would like to, which is a direct measure for determining chaos in classical systems, and we'd like to see how that actually changes as a function of E over n square. So here you see the plots for the Lyapunov exponents. So the subscript for lambda 1, lambda 2, lambda 3 refers to the models at matrix levels n1, 2, 3, and so on. So n being the small n, so that is related to the matrix sizes by the fuzzy four-sphere dimension formula. So that means that, for example, this lambda 2 is computed, the reduced action for the lambda 2 comes from taking trace of 10 by 10 matrices, whereas for lambda 3, that is 20 by 20 matrices and so on. So, well, it turns out that at the n equals to 1 level, which is corresponding to the 4 by 4 matrices, no chaos survives at sufficiently high energies. So that model is separated from the rest of the models. And we like to focus on the models starting with 10 by 10 matrices and higher in this setup. And the fitted curves here, I will motivate this further as we go on, are given in this form, where E and F are the fixed point energies, which are all negative. So these are also the plots for n equals to 4, 5, 6, and 7. As you might note here, n equals to 7, the fitting curve in the n equals to 7 case is not all too well. That might be related to the fact that the reduced action for the n equals to 7 case was extrapolated from the results that we have obtained for the previous models. So that might be one reason. But let's go on. And these are for the mass squared values of -16 and -2. And I will show you other results for other mass values as we move on. So, and from the energy dependence of these Lyapunov exponents, we would like to pass to analyze the temperature dependence of these Lyapunov exponents for these family of effective actions that we have obtained. So in order to do so, we actually adopt some considerations that that were actually used in the pure BFSS model, which goes as follows. Well, by using the virile and equipartition theorems, it is possible to relate in the BFSS model the total energy to the number of degrees of freedom times the factor of 3/4 times the temperature, as you can see from these relations. And the number of degrees of freedom can be counted from the original setup of the degrees of freedom given by the Hermitian matrices, but taking into also the consideration the Gauss law constraint and the global symmetries. So at large n, the number of degrees of freedom goes like 8n squared. And as I have noted also in the motivations part, in the work of Gurari and the collaborators, the Lyapunov exponent was determined to be being proportional to the 1/4 power of the temperature, and the coefficient that relates is found from numerical work to be 0.29, which leads to the result that below or above this temperature of 0.015, the MSS bound is well satisfied, but below this temperature it is violated. So we would like to adapt these considerations, as I have noted. Since we have massive deformations in the model that we are considering, as opposed to a purely quartic potential, the virile theorem won't give us this equality. Instead, it will give us, some inequality that will stem from one of these equations, either from the clubs or the spades. So we can write these two equalities, and you see that from the clubs, since Xi Hermitian matrices. So we can see that the clubs tell us that the kinetic energy is larger than the potential, whereas the spades tell us that for masses which are tachyonic, we have that the kinetic energy is larger than twice the potential. So for the present case of mass squared values of -16 and -2, the second inequality is more useful. And since we have already set the X9 matrices to 0, the original degrees of freedom can be counted to be 7n² in the large n squared limit. And that gives us a bound on the energy in terms of temperature, or E/n² in terms of temperature, is given in this inequality. And therefore, now we can go back to the fitting curves that I have just displayed in these plots previously. So this functional form is well motivated due to a few reasons. One of them is that well, we have first noted that these models started to develop chaotic dynamics only after the fixed point energy value is exceeded. And this fixed point energy implicitly is determined by the mass values. So this is how these dimensionful parameters are coming into the play in this model, or determining the chaotic dynamics. Details of the chaotic dynamics. And furthermore, the power 1/4 in this equation is suggestive from the energy and also temperature dependence of the Lyapunov exponents in the pure BFSS model. And further, this relation between the Lyapunov exponent and the 1/4 power of energy is inferred for a homogeneous quartic potential due to scaling. So this is a well-known fact for such models as well. So the new ingredient here is the fixed point energies, which we have introduced into this equation in the manner that is shown in this equation. So the conclusions from these considerations are as follows. We see from this inequality that at 0 temperature, the energies will be less than 0, but the Lyapunov exponents won't vanish for energies which are larger than the fixed point energy and less than 0, which tells us that at 0 temperature, the MSS bound will be violated. And so this is one interesting fact. And furthermore, we can put an upper bound on the temperature below which the MSS bound will eventually be violated. So to do so, we can replace the E/n² with this upper bound on E/n², which is E21/4 times T. And from here, we can put an upper bound by solving the equality condition or the saturation condition. And this gives us the following results, which are outlined in the middle column of this table. So, and these results are upper bounds for the temperature. It is not necessarily the temperature at which the MSS bound is violated, but there will be a temperature below which it will eventually be violated. And if we compare this with the BFSS case, we see that they are of magnitude higher, order of magnitude higher than the 0.015. So very quickly, I can tell you how just some other different mass values can alter these considerations. And one particular question that we could ask is, what happens if we choose mass squared values, which leads to the result that these H1, H2, 0, 0 are not fixed points, but only fixed point is given by this all zeros. So one possible choice that fulfills this requirement is given by m1 squared minus 8 and m2 squared is 1. And well, in this case, since the fixed point energy is 0, then for the fitting curves, it is better well, it is reasonable to look at this functional form. And here are the results. For n equals to 1 case is still that it won't lead to chaos at large energies. But you see for other cases, there is also chaotic dynamics, and we see how it goes, it develops with E over n squared, and the fitting curves are in fact somewhat better than what we have found for the previous mass values. And again, by using the equipartition and the virial theorems, we can put an upper bound at the temperature below which the MSS bound is going to be eventually violated. You see that since one of the mass squared values is positive here, we use well, this condition. So the second condition is not valid, but the first condition coming from the clubs are still valid. So that is what we use in that analysis. So, and this leads to upper bounds on the critical temperature, which are given by the column in the by the middle column in this table. So these are closer to the values that are obtained in the BFSS model. They are just about twice of what is obtained for the BFSS model. And let me also very quickly tell you another form of the ansatz, just to compare how things could change if we just take an ansatz, which is the fuzzy two-sphere part of the ansatz is different in the sense that it is not just one big fuzzy sphere which fits into the dimension of the matrices that we take for the fuzzy four sphere, but it is composed of a direct sum of the smallest fuzzy two spheres. So that is like we did this for several different values of the matrix sizes. So you fill in the ansatz part for the fuzzy two sphere by block diagonal 2 by 2 matrices, which are corresponding to the fuzzy sphere at the lowest angular momentum level. Well, the analysis is similar, but it turns out that only this 0, 0, 0 is the only unstable fixed points in these models. And it turns out that the chaos is limited to some energy window. So if we keep on increasing the energies, eventually the chaotic dynamics will fade away. And this is also visible from the Poincare sections. So in the at some energies, initial energies, you see that there is no chaotic dynamics, only quasi-periodic orbits. In the middle column of the plots here, you'll see that there's some chaotic dynamics is present. But if you keep on increasing the energies, then the chaotic dynamics ceases away. So I think I'm coming toward the end of my time. So I will not talk about the recent results in the AVHM model. Maybe I will report them on a probably another talk in Corfu, hopefully. So let me pass to the summary of my results. So we have studied the onset and development of chaos in mass-deformed Yang-Mills matrix models. The main result of our analysis is putting upper bounds on the temperature dependence of the Lyapunov exponents. And we have just seen that at temperatures below such critical temperatures, the MSS bound will eventually be violated, whereas for T larger than Tc, the MSS bound is safely satisfied. And maybe just a few comments regarding a comparison of the first and the second ansatz from a broader perspective. So in the first set of ansatz, we have a maximally large fuzzy two sphere which fits into the given matrix, which is just given by the given matrix size. Whereas in the ansatz 2, we have lots of the smallest fuzzy spheres, which are given by 2 by 2 matrices. And in the latter case, the chaotic dynamics fades away at large energies. So this tells us, in a sense, that the chaotic motion is favored in configurations in which there's a big blob of a fuzzy sphere, a big blob of a fuzzy two sphere, than those in which small bubbles of fuzzy spheres are present. So this can also be seen as if we have blocks of fuzzy 2x2 fuzzy spheres, this actually kills the interactions among the D0 branes in some directions. That's because the off-diagonal entries of these matrices are the stringy excitations between these D0 branes. And so this makes a difference. So we can view this from a little different point of view as well. So we can try to see how the size of the fuzzy spheres affect the development of chaotic dynamics. And and there are some further remarks that can be put forward in this direction, but I don't want to exceed the time allocated for my talk. So I'd like to stop here, and thank you very much for listening.
Questions from the audience? Please, Filev.
I'm sorry?
Filev is going to ask you a question.
Okay, okay.
Hello, Seckin.
Hello.
Gaetano Seidan Fedele.
Yes, hi, Fedele.
I don't really understand why it is talked of chaotic behavior, because a positive Lyapunov exponent doesn't mean chaotic, and exponential growth has a positive Lyapunov exponent, but it's not chaotic. Now, you have shown probably the eigenvalues, that this would be quantum chaos, but in general, I don't see what's chaotic there.
Oh, here we are just looking at classical chaos. So a positive Lyapunov exponent in the classical chaotic dynamics, a positive Lyapunov exponent, even a single one, is sufficient to conclude that there is chaotic dynamics.
No. You take e to the t, e to the alpha t.
Yeah.
You take two initial conditions which are very close by, and
Right.
they will fly away exponentially far
Right.
away, but it's not chaotic. Chaotic, chaotic is not a well-defined definition, but positive Lyapunov is not the same as chaotic.
As far as I know, the literature in classical chaos, so this is one of the supplementary slides that I have,
it's necessary, but it's not sufficient. There are counterexamples of positive. There is not a good definition of chaotic. But
so yeah, there could be some. I don't know the literature completely, but at least in the in Hamiltonian dynamics, at least this is the literature that tells that even a single Lyapunov exponent, positive Lyapunov exponent, is sufficient to say that there is chaotic dynamics. But if the system is not a Hamiltonian system, there could be other considerations as well.
Because of the conservation of area can be sufficient. I don't know.
Yeah.
Okay, thank you anyways. Thank you.
Mm-hmm.
Okay. Any other question? Please.
Hello, this is Juraj Tekel. I had 3 questions, but you managed to answer 3 minus epsilon towards the end of your talk. Is the configurations that you considered, both ansatz, are they stable against the quantum fluctuations in the model? Or is this related to the last point that you made?
Let me just state again that we haven't considered any quantum fluctuations. So this is purely classical. Everything we did in this work is classical. So the point is that this classical dynamics is good to approximate the quantum dynamics in the large and high temperature limit. So, and as a indication of that, we look at the comparison of the of this Lyapunov exponent with the temperature dependence of a quantum chaotic Lyapunov, or the quantum Lyapunov exponent, which is bounded by 2 pi t in the MSS conjecture. So since the treatment is classical, it is natural that at some temperature, eventually, the bound is violated. But the analysis is good, and it complies with this quantum chaos results at sufficiently high temperatures. So I don't know whether this answers your question, but maybe I can add one further remark, which I didn't have chance to tell, but there are some recent results due to Vidovich and collaborators, which extends the classical treatment to quantum treatment by an approximation called the Gaussian state approximation. And in that analysis, it can be shown that the Lyapunov exponents vanish at a finite temperature, so the MSS bound is always satisfied.
Thank you very much.
Okay. No more questions from the audience, and I think also from remote. So I will start with the next talk, which.
Okay, thank you very much. Shall I?
And the title is Non-perturbative investigations of gauge theories with adjoint and fundamental matter related to supersymmetric gauge series. You are there? Yes, Georg?
Yes, can you hear me?
Okay, please.
Yeah. Can you also see the slides?
Yes, we can see your slides.
Ah, very well, thanks. So thank you, and thank you for the opportunity to present our work at this nice workshop. I hope I will soon be able to visit also Corfu in person again, because it's really it has been really a nice place to visit. Today I will present some work towards a more general goal of simulating supersymmetric gauge theories in 4 dimensions, and I will hope to convince you that it is also interesting to look at more general theories, in particular gauge theories with adjoint matter and fundamental matter, so a kind of mixed representation setup. This work has been done in collaboration, in particular with Stefano Piemonte. So towards in general, this talk will be a kind of an overview, so I will hide several technical details, so don't hesitate to ask anytime if you want to know more about. So in general, the simulations of supersymmetric gauge theories, or in general a non-perturbative investigation of those theories in 4 dimensions is quite difficult, because the most straightforward approach, which are lattice simulations, are difficult to make for this kind of supersymmetric theories, which is basically due to the fact that supersymmetry is related to the symmetries of space-time, and this is broken by the discretization. And you in general don't get these symmetries back in the continuum limit with a finite lattice, and but instead you have to add fine-tuning terms to the action and fine-tune the parameters in order to achieve the supersymmetric point in the continuum limit. And this is, in particular for theories with scalar fields, it's a very difficult fine-tuning problem in 4 dimensions, whereas in lower dimensions, these kind of theories can be easily solved. There are particular approaches. I will also talk a little briefly about them in the last part. that apply for n=4 supersymmetric Young-Mills theory. But there's an additional difficulty, and this is to study the conformal invariance on the lattice. So most of these theories are believed to have conformal invariance, at least in certain parameter regions, like the n=1 super QCD, which a certain number of flavors, or n=4 super Young-Mills theory. But it is quite difficult to handle this, or unknown how to handle in general this conformal symmetry on the lattice. So you need some kind of float away from the regulated theory to get rid of the lattice artifacts, and then you have another scale until which you can follow the RG flow, and this is the this is given by the lattice volume that you have in your numerical simulations. And in QCD, we have quite good confidence how this evolution is and how we get rid of the lattice artifacts, because there we can use asymptotic freedom to describe this. But in general, it's quite difficult for general theories, in particular if there are expected conformal fixed point. So therefore, it's actually interesting to consider more general theories and not focus just on the supersymmetric examples, but to study more generally these gauge theories in 4 dimensions. And there's another motivation which comes from the fact that from the theoretical side, one wants to. There's a lot of effort to generalize the things we know of supersymmetric theories towards more realistic theories, and therefore to get away from the supersymmetry and to consider more general cases. And in that way, one can hope to meet even in between, to have the numerical approaches that are able to sort of check and maybe also generalize these conjectures that have been made based on these supersymmetric theories. And in particular, I will be talking about this kind of setup. So you have a gauge action, and then you have a certain number of flavors, of fermion flavors in the fundamental representation, and then in addition a number of flavors in the adjoint representation. They are coupled via the gauge sector only. In super QCD, for example, you would have in addition scalar fields that couple these kind of theories. As I said, these theories are motivated by a generalization of supersymmetric theories, and then they have also been proposed in composite Higgs scenarios, where you try to explain the Higgs sector with an additional strongly interacting theory, and these kind of theories have been proposed for these kind of scenarios. And then, which is basically what I said concerning the theoretical approaches, there's also being a consideration of these models in the work of concerning quantum distillations and a color flavor center symmetry, which can be realized in the theories. And this is a kind of theoretical approach that tries to get away from the supersymmetric counterparts and derive some more general statements about gauge theories. So concerning the supersymmetric gauge theories, it's very natural that you always need an adjoint fermion in these theories. We're counting here Dirac flavors. Therefore, the Majorana flavor that you need for the supersymmetric super Young-Mills theory, so as a partner of the gauge fields, would count as a flavor number 1/2 in this case. And the pure gauge sector is basically just the gauge field and a Majorana fermion in the adjoint representation. Then if you want to extend this, the most straightforward extension is to couple it to a matter field. But in supersymmetry, you need also, besides the quark field, also the squark fields as a partner field. And if you then just break supersymmetry and add an artificially high, heavy squark field mass to the theory, then you arrive at these kind of theories that I have presented, just with the fixed flavor number in the adjoint sector of 1/2. Similarly, you can also derive n equals 2 super QCD by considering no fundamental flavor sector and just one Dirac, one adjoint Dirac field. The pure gauge sector has been already extensively simulated on the lattice, and there are actually quite good data from the numerical simulations. We have obtained bound states masses, and we have shown that we can obtain the supersymmetric continuum limit. But as I said, if you then to do the most straightforward extension and add the squark fields to the theory, then you add up with an order of 10 additional counterterms that you have to add and fine tune. Whereas in the case of superangles, there's basically only one counterterm that you have to consider and to fine tune to reach the supersymmetric continuum limit. Now, as I said, the second motivations are composite Higgs scenarios. In these kind of approaches, especially when considering what is called minimal walking technicolor or general walking technicolor theories, one wants always a kind of near conformal theory, and this means one has to add a lot of fermionic fields to the theory to arrive as a near conformal or walking behavior of the gauge coupling. But in order to keep the number of flavors minimal, which is good for phenomenological reasons, one can also switch to other representation, in particular the adjoint representation. It turns out that if you consider 2 flavors of adjoint fermions, you end up, or at least this is what lattice simulations have been suggesting, end up as a very conformal theory already. And therefore, it would be better for phenomenological reasons to consider the one adjoint flavor case, but this cannot be coupled straightforwardly to the standard model. Therefore, in this case, in order to have a real composite Higgs scenario, you would need what is called ultra minimal walking technicolor, which is 2 fundamental flavors and 1 adjoint Dirac flavor. It's a minimal setup. There are further theoretical reasons why the one flavor adjoint Dirac fermion has been investigated numerically very recently. And this is a possibility of very different infrared scenarios for this theory. First of all, this theory can have chirosymmetry breaking and be a QCD-like theory with pion-like states as lattice particles. But it can also have, as I said, a kind of conformal infrared fixed point, which means that all masses are scaling according to the same mass autonomous dimension. But there's a more exotic scenario which has been recently proposed and which is based on an analysis of 'T anomaly matching in this theory. And this is a light baryon scenario where a baryonic state becomes the lightest state, and you have light fermions in the infrared in this theory. And this has motivated quite some studies I have listed here. Besides our studies, there's also been a group at MIT following this analysis. And in the conformal case, of course, the motivation was always that one wants to find somehow the lower bound of the conformal window in the with adjoint fermions. Even though this has been extensively studied already on the lattice, there's not yet a conclusive solution here. I just show here some particle spectra that we have obtained for this theory. It seems that you have, on the one hand, something that is consistent with conformal scaling, because what you expect is that you have only a weak dependence on the fermion mass in this case if you plot ratios or dimensionless quantities on this these kind of plots, because they scale always the same mass almost dimension in the conformal theory case. But there's a remnant gauge coupling dependence, and this is stronger than expected from the conformal picture. Therefore, it's not really conclusive overall. What is also consistent or very interesting in this case is that we observe a very light scalar in this theory, which seems a particular feature for these theories with adjoint fermions. And then I talked about the last point that motivates studies of these kind of theories, which is a color flavor center symmetry. Usually, if you look at QCD, then the phase transition, the deconfinement transition, is only a crossover because you have a breaking of center symmetry. If you now switch to a joint matter, then you preserve center symmetry and you observe a real phase transition. And this has, and in addition, you can also switch the boundary conditions to periodic boundary conditions instead of the temporal ones. And this allows to compactify the theory to a small circle and still stay in the confined regime and investigate in a semi-classical approach the deconfinement transition. This is, in fact, a generalization of the Witten index for non-supersymmetric theories. And this is, in fact, what motivates studies that go under the name of quantum distillations. And of course, one approach is, or one interesting route is now to extend this towards theories that are that involve also fundamental flavors like QCD. And you can, in fact, preserve the center symmetry by looking at a combined center flavor symmetry for a certain number of flavors. And this has been proposed in several works to investigate the semi-classical confined regime in a more general sense, and to have this generalization of the Witten index for non-supersymmetric theories. Okay, and I hope this is enough to explain there are several routes of motivation for this kind of studies of theories that involve fundamental and adjoint flavor theories. And we have done a study with which involves basically one adjoint and two fundamental flavors. And we have used some improved fermion actions to do these simulations, and the symmetry breaking pattern is different from QCD because we have SU2 gauge theory here involved. Therefore, you have the breaking in the fundamental sector SUN to SPN, and in the adjoint sector you have breaking of chirosymmetry, which is consistent with this adjoint nature of the fermion fields. And this should be compared always with the alternative scenario that you have a near conformal behavior, or even that you can have this light baryon scenario that has been proposed. First of all, what you always need to investigate in these kind of theories, if they can be conformal, is if there are artificial lattice transitions. And indeed, for these adjoint theories, you find in a certain range of the gauge coupling some artificial phases that you need to separate out, and which limits a lot your your possible investigations. And we have also made some consistency checks with the pure fundamental theory, which has been simulated in earlier works. Here is shown the vector mass in this as a function of the basically the current quark mass, and you see that it scales in a certain way, in a certain limit, at least quadratically to the chiral limit, and you can obtain very nice results, which is consistent with the well-known results there. Now you can add this additional representation, and you observe that you get an additional dependence on the second current quark mass. So you have not only the dependence on the quark mass in one representation, but then you get a non-trivial dependence on the quark mass in the other representation. And there have been effective theories, basically generalization of chiral perturbation theory for this two representation setup, which involve additional fits for the additional quark masses. But what you and we have done these fits, they work quite nicely for this theories. What you can see is that in particular the dominant contribution or the dominant dependence seems to be rather from the adjoint sector in these kind of simulations. So this seems to be the leading dependency of this approach to the chiral limit. And now one can confront this with a conformal scaling scenario, but you have to generalize this first to a setup where you have two mass parameters. The mass deforms the conformal scaling, so you won't reach the fixed point, so you have to consider a scaling that includes these mass parameter. If you are close enough to if your trajectory is close enough to the conformal fixed point, then you know basically that every mass scales with the same mass almost dimension here, which comes basically from analysis of the scaling of the correlation function. And you can generalize this to theories with two different representations, and which provides a more complicated functional form, which is listed here. And basically you have now two different directions that are relevant from the perspective of the fixed point, which is the mass of the fundamental and the adjoint representation. And you have to consider both of them in this scaling formulas. And we have done now, and so we have, in order to compare this to the chiral fit, we have also done a fit according to this scaling by considering different parameters for the ratio of fundamental and adjoint representation. But if you compare this to the first approximation, which would be a dependence on one of these scaling corrections, or this mass of dimensions only, then you end up at a very different value, and in fact you arrive at something that is not consistent, no consistent picture in this way with a conformal scaling of these theories. So the conformal scaling of this two representation theory is, according to our simulations, rather disfavored in this case. Now, let me talk a little bit more about the general problem with conformal scaling on the lattice. It is in general a controversial problem because you have to approach somehow the continuum limit, and then the question is whether the fixed points that you see in this kind of approach are independent of the lattice formulation that you choose. So basically, during the flow, you need to have certain control over the irrelevant direction, and you need them to vanish. Basically, that you that these irrelevant parameters that are basically a parameterization of this lattice, this choice of the lattice action, that they die out and that you approach some universal continuum limit. And there have been always a question whether, for example, staggered fermions you obtain, which is a particular difficult fermion formulation, which whether you obtain the same fixed point as with other formulations. And it did, of course, in addition, you have the technical problems that you have to get to control the other parameters, the other scales in the system, that, like the mass and the volume, that breaks the scale invariance. It is in particular a difficult problem if you consider n=4 super-Yang theory, because basically you should have no running of the gauge coupling there for any value of the gauge coupling, which means you would have to a line of fixed points that you approach depending from where you start, and you have to get still rid of the artifacts that are introduced by the lattice realization. And I find this very interesting, in particular towards the lattice simulations of n=4 supersymmetric Yang-Mills theory. In that case, in fact, a lattice formulation is possible because you can preserve, due to the large number of supersymmetries, you can preserve a subgroup. You can basically preserve one supersymmetry. And it has been shown that this reduces the fine-tuning, so you can approach the correct continuum limit without a severe fine-tuning problem. But this continuum limit is still quite non-trivial, because you have to approach this scale invariant fixed point. And also at that point, the beta function and also a possible mass dimension should vanish in this limit. Even though the conformal invariance is basically broken by the lattice. And together with David Shake, I've done in that respect an analysis of the renormalization group flow of the mass dimension, which is obtained on the lattice from the spectrum of a Dirac operator. And what you measure basically is something that should be zero, no matter independent of the gauge coupling. But here is it shown how it evolves on the lattice with a certain cutoff introduced to the eigenmodes of the Dirac operator in order to have a scale in this quantity. So you see here basically the scale dependence of the mass dimension. And you see that for a large number of couplings, it stays in fact very small, and even in the infrared, it goes to zero. But if you increase the gauge coupling, you need a much longer running, so more scale to separate basically the lattice artifacts and the infrared scale, which is given by the lattice volume basically. So and this shows that, in fact, for this theory, this approach to the fixed point in the continuum is actually also very non-trivial and requires further investigations. So this brings me to my conclusions. I've shown you that it's interesting to study more general gauge theories than just QCD, and also not to focus first directly on the supersymmetric theories, but also to study some related theories, which are theories with mixed fundamental and adjoint matter. They have several different applications, and they presented the first study which favors rather a chirosymmetry breaking behavior, but it's still quite close to the conformal scaling. In addition, of course, it would be interesting as a further step to investigate also the phase transitions of the theory, in particular to this quantum distillation and the possibility of having this preserved center symmetry in this theory. As a last point, I also mentioned how the conformal continuum limit of n equals 4 super-young moles is approached, and this requires really careful analysis, and that's a very non-trivial way to represent this on the lattice. So thank you for your attention.
Is there any question from the audience? I don't see any question from remote. So it's a good time to have a coffee. So we reconvene at 5:30 after the break. Okay, thank you. Yes. So it's time to start again. I see the first speaker, who is Veselin Filev, and he will talk. The title of his talk will be Backreacted D0 or D4 background. Please proceed.
Thanks. Thank you for the opportunity to speak. It would have been much better, of course, to be in person, but let's hope next time it will be in person. So, as you already heard, the title of my talk is Backreacted D0, D4 background. It's a work that we did together with Denjo O'Connor and Yuma Asano. Now, I will begin with a very brief, indeed, reminder what the ADS-CFT correspondence is and how we add flavors to the correspondence, what techniques we use to add the fundamental flavors. And then we're going to focus on the D0, D4 brain system, which gives us a lower dimensional version of this flavored ADS-CFT correspondence, which our collaborators, my collaborators and I tested on a computer with some papers. And now what we want is to construct a fully dynamical background, which is backreacted. And so we're going to talk about the uplift of the D0, D4 background to 11 dimensions. And we're going to use the Garfinkel-Vachaspati construction to construct the backreacted geometry. And then we're going to revisit the D2, D6 brain system, which is work done by Cherkis and Hashimoto back in the 2002. And we're going to want to learn some lessons there and then apply them to the partially smeared D0, D4 system, which is our final solution. So it is probably a bit redundant at this point, but still, as we all know, the original correspondence of the ADS-CFT, the original formulation of the ADS-CFT correspondence is a correspondence between type 2B string theory on ADS5 x S5 background and N equal 4 super Yang-Mills theory. And the way we quantify the correspondence is through the Klebanov-Polyakov-Witten formula, which relates the generating functional in the CFT theory to the tree-level partition function in supergravity. Now, in this original formulation, there are only adjoint fields. There is no fundamental matter. And there has been some work, actually quite a lot of work, dedicated to applications of the ADS-CFT correspondence with fundamental matter. And there are various ways to introduce fundamental matter to the story. And one way is due to Cherkis and, Karch and Katz back in 2003. And it is inspired by the properties of the D3, D7 system. So the D3, D7 system, the D3 brain, D3, D7 brain system, when you look at the low energy effective field theory that governs it. As we know, for the D3 brains, this is the N equal 4 super Yang-Mills, and in fact, this is how the N equal 4 super Yang-Mills end up being the first theory to be holographically studied. And now, but when you introduce these 7 brains, you actually add flavors to the story, and the low energy effective field theory here is N equal 4 super Yang-Mills, now coupled to N equal 4 to N equal 2 hypermultiplets, fundamental hypermultiplets. So there are these strings that stretch between the D3 and D7 brains that give rise to the fundamental hypermultiplet. And the separation between them gives the mass of this hypermultiplet. So the idea was now to study this in the context of the ADS-CFT correspondence is to imagine that we have a lot of D3 brains, a stack of D3 brains, and we kind of replace the D3 brains with the near horizon geometry. And while doing that, we keep the D7 brains close to the horizon, and so we end up with D7 branes probing probing ADS5 cross S5 space. So that was the prescription. The prescription was to use Dirac-Born-Infeld action to study probe branes, and these probe branes are treated as flavor branes, and the field theory can be learned by looking at the flat version of the D3 D7 system, but this can be done also for D3 D5 with a defect. And it has been very fruitful. There are many, as I said, papers written on that with a lot of physics intuition gained from them. And what we wanted was to test this, but it was very difficult, as the previous talk, in fact, illustrated. It is very difficult to simulate any Q4 super Young mills, and it would be probably even more difficult to do that with flavors, because they would break some of these symmetries that the Q4 super Young mills have, that some groups use to help them simulate it. And so that's why we looked at the lower dimensional version of the correspondence, which is the D0 D4 system. In fact, it's T-dual to the D3 D7 system. So all these nice properties that I said about n equal 4 super Young mills coupled to n equals 2 hypermultiplet, I mean, they're more or less apply for the T-dual systems also. So the corresponding adjoint theory is coupled to n equal 2 hypermultiplet. And in this case, in the case of the D0 D4 system, the dual theory is a flavored version of the BFSS matrix model, and it's in fact well known, and it's called the Berkus-Douglas matrix model. It was originally formulated to introduce M5 brane density to M theory, but it works in 10 dimensions. It is D4 branes. So now, the nice thing about this theory is that it is it is one-dimensional. So it's quantum mechanics, essentially. And as we know, that means it's super normalizable. And so we avoid the fine-tuning problem. I mean, this has been motivation for many, research papers, that you focus on the D0 brane part, so only the adjoint sector. What we did was we introduced flavors also in the game. And one thing to say here is that when you start simulating this model, it's not impossible. I mean, it turns out it's actually, we did simulate it. But the natural thing to do is to simulate the full the full dynamical model. And what you actually study with this probe brane scenario that I described is a kind of quenched approximation. So it's an approximation in which you keep only one fundamental loop in your partition function when you expand your partition function. And so this is not fully quenched, so you don't kill the full fundamental determinant, but it is quenched. And if you want to unquench it, you effectively have to consider back reaction of the flavor brane. So this is what motivates what comes next. So to go beyond the quenched approximation, we need a fully back-reacted D0, D4 geometry. And for various reasons, it's actually easier to do that in 11 dimensions. So rather than, type 2A supergravity is 10-dimensional, but rather than doing that, we go to 11-dimensional supergravity, where the D0 brane uplifts to a KK momentum and the D4 brane uplifts to a M5 brane. And the technique that we use to construct the solution is due to Garfinkel and Vachaspati. It's not needed to use this technique. And you could just do straightforward tedious super symmetry, and then use, let's say, Einstein equations or charge conservation, and you can get the ansatz for the metric and the equations of motion. But it is much faster to do it that way. So what is the Garfinkel-Vachaspati construction? Now, it is a solution generating technique, and it applies for theory with such action. And as you can see, the 11-dimensional supergravity is part of these theories. So it can be applied for 11-dimensional supergravity. Now, what are the requirements to use that generating technique? You need to have a killing field, and this killing field also need to be hypersurface orthogonal. So this second, well, it needs to be null, and the third condition is the hypersurface orthogonal condition, where S is some scalar function. Now, if you have such a killing field, then the following deformation of the metric is also a solution. That's the claim. And here in the deformation, S is the scalar, psi is a new scalar, and psi satisfies these two conditions. Like the second is just the Laplacian, just the harmonic equation. So we're going to use that. And as a warm-up, we will start with flat space. So let's consider flat space in 11 dimensions, and we're going to use the GA construction to obtain the uplift of the D0 brane. I should mention that this was used by Rangamani and collaborators, this technique, to explore possibilities for black PP wave background, stuff like that. It is very similar what we do here, but we use it in a slightly different regime and get different results. Now, so we start with flat space, and this is just radial coordinates in flat space, and we introduce standard light cone coordinates. And now it is easy to see that one of the light cone directions, well, in fact both, but we choose one, satisfy the requirements for the GA construction. So the vector field DDX11 is a hypersurface orthogonal killing field with scalar function S equal to 0. And just for historical reasons, we replace the scalar function psi with H, because H will become now the usual warp factor for the D0 brane background. And so we construct the following geometry. We consider the following deformation, and this is the new geometry. And you can recognize this geometry as the uplift of D0 brane. So if you reduce that to 10 dimensions, you're going to get the D0 brane geometry. Okay. Now, what we wanted was to construct backreacted D for D0 brane background. We know that D4 branes uplift to M5 branes. We started from flat space, and we were able, with the GA technique, to kind of induce D0 brane KK geometry there. So perhaps we could do that with starting with the M5 brane geometry, and we're done. And that's what we do. So we use the same strategy. We start with the M5 brane geometry, and we introduce light cone coordinates. And now again, the DDX11 vector field is hypersurface orthogonal killing field. So the GA construction can be applied, again with S equals 0 and psi equals H. And the final form of the metric that you obtain is the following. And this is the ansatz for the uplift of the D0 D4 background. As I mentioned, you could arrive to that using only supersymmetry. So if you require to keep the appropriate number of supersymmetries, this ansatz comes to you. Of course, you also have to fix the warp function for the M5 branes, but that follows from charge conservation and symmetry. And so when you reduce to 10 dimensions, this is the metric that you obtain with the corresponding dilaton and Ramon field and fields. All right. Now, okay, but this just gives us the ansatz. So what about the solution? Now, what about the equation of motion? Well, remember we had this harmonic function here, right? So this is nice. And in fact, that is our equation of motion, just Laplacian of H. The other is trivially satisfied. The other equation one can check. Now, as I mentioned, it's not needed to go that way. You could have, I mean, you could obtain this in at least 2 ways, or maybe 3 ways. You could write Einstein equations, it will follow. You could use angular momentum conservation in 11 dimensions, it would follow, or you could use Ramon-Ramon charge conservation in 10 dimensions, it would again follow. But with the GA technique, it is just automatic. Now, unfortunately, this equation, even though it looks very innocent, cannot be solved analytically. Now, and before we embark into solving it the best way we can, I would just mention that localized D0, D4 brane solution, when the D4 branes and the D0 branes are on top of each other, does not exist. The D0 branes cannot be localized inside the D4 branes. There are some papers from the late 90s or mid 90s by Michael Duff and collaborators, if I'm not mistaken, that show that the D0 branes will become unstable and they will dissolve inside the D4 branes. And this makes it very tricky to actually impose physically the boundary conditions and fix your constant of integrations. And that's why we look for examples where you don't have this complication, with which we can experiment and check that our approach works. And one such example is the D2D6 brane geometry. So we revisit the D2D6 system. This is by Cherkis and Hashimoto, constructed back in 2002. It has the following answers for the metric, and the function h satisfies this harmonic equation. Now, this equation, as you can see, has Coulomb potential, and it actually can be solved, well, almost analytically. What you can solve analytically is the Fourier transform of the function h. So the Fourier transform of the function h, this equation, now can be solved analytically. And they did it. They solved that equation. They showed that the regular solution is given in this form. And here the non-trivial part is to fix the constant of integration. And notice that this, since it's a Fourier transform, this constant of integration actually prescribes the whole solution. It's not just a constant. After you do the back Fourier transform, it could give you an entirely different function. So it's very important to fix it correctly. And what they used is, they said, well, in the limit when this parameter m, which is linked to the Taubnat geometry that you have in 11 dimensions, you have the Fourier transform approaches the Fourier transform of the warp factor for the M2 brane geometry. So they have this specific requirement, and it's inspired from the physical realization that in that limit, when you focus in the interior of the Taubnat geometry, it flattens, and the 11-dimensional space becomes just M2 branes with transverse flat space, so just M2 branes. And most symmetric solution is just the solution of M2 branes. So in this limit, they can match the solution to M2 branes, and that's how they fix this constant. And okay, now this just summarizes what I just said, that the authors use 11-dimensional uplift of D6 branes, which is a magnetic monopole to realize this Taubnat geometry. But we don't have that luxury in the D0, D4 system. Now, so in order to be able to obtain a solution, we will rederive their geometry in a different way. So what we do is we separate the D2 and D6 branes and then smear the D6 branes just in the space orthogonal to the D2 branes. Now, this will create a cavity in the geometry with no D6 branes density. And now, using, the analog of Berkov's theorem in GR. We know that outside of that cavity, because we restored symmetry by smearing, the solution should be the same as that of well, the equations of motion should be the same as those for the Cherkis-Hashimoto case with no smearing. And inside, there will be no D6 brane density. So the vacuum equations of motion should be the same as those for only D2 branes. Of course, the constant of integration will be different now. Or you can represent that with this diagram. So you have the D2 branes, and then you have the D6 branes. The D6 branes here would be represented by a localized D6 brane would just be a line. And now when you smear them, it becomes a cylinder. And this is your cavity. Inside the cavity, you have D2 brane solution. Outside, you have the full solution, and you have to match the constant of integration. The way you match the constants of integration is you require continuity at the shell. And so inside, as I said, you have the following ansatz. The work factor here is just constant. And you can, in fact, hit it in redefinition. And you see that with the appropriate coordinates, you can write this to look exactly as the D2 brane metric. And then the most symmetric solution is given by this. Here, we have changed slightly the constants that gives the charge, etc. But other than that, it's the same solution. And now you can go back to the original variables and Fourier transform. And now we have the Fourier transforms, the solution inside the geometry. Now, outside of the geometry, we know that the equation of motion is the same as Cherkis and Hashimoto considered, and it will have the following regular solution. The only difference now is the constant of integration, BP. It will be different. And now imposing continuity at the shell, and we can fix the constant of integration. And now if everything is consistent, when we shrink the cavity to 0 size, then it won't matter that the D6 branes were smeared. We should recover the solution of Cherkis and Hashimoto. And indeed, one can take that limit and convince themselves that that's the case. So this exercise, we did just to be confident, because you cannot do that limit for the D0, D4 brane case. It's unstable. And so we wanted to make sure that it gives meaningful result, at least in one case where it's tractable. And also, you can look at it in another way. We, instead of using idiosyncratic condition, which was the fact that they had this Taubnat geometry, which gave them the physical requirement for M2 branes in that particular limit when the Taubnat flattens, we can always do that. We can always introduce cavity, and we can always impose continuity at the cavity. So this is a more general approach. Clearly nothing new, but we applied. Okay. So let's do that for the D4 branes, for the D0, D4 branes. So we start with the D0 and D4 branes. We separate them at some distance. This distance, by the way, will be the mass of the hypermultiplet. And in the dual field theory. And now, well, provided you take near horizon limit. Now, what we consider now is before you take near horizon limit. And now you smear. And then you obtain the cavity. It's exactly the same exercise. So to obtain non-perturbative solution, you need to match this boundary. You have to impose boundary conditions at the cavity. And so we separate the D0, the D4 branes from the D0 branes, smear them. And the flux for the D4 brane density, the field strength, is given by the following expression. Now, inside the cavity is just constant, represents the fact that there is no density. There is not density, but there is no, there is no D4 brane density. So it's just constant field strength. So 0 Ramon form. Well, the opposite, sorry guys, the opposite. This is the form. Yeah. The field strength is 0. And outside it is the same as if you didn't have any smearing. And now, this is again, I commented for that in the D2D6 case, it's exactly the same logic. It's analog of Berkov's theorem. And now you scale your geometry inside the cavity, and it looks like that. It looks like the solution for D0 branes, but it has slightly different constants. I mean, you can arrive at these constants using charge conservation arguments. And now the most symmetric solution is then given by the following expression, and you can Fourier transform it and feed it into your equation of motion, and use it as a boundary condition at the cavity. So now you have two choices. You can solve this equation, which is the Fourier transform of your equation of motion numerically, and you can match with the solution that you have at the cavity, shoot to infinity, and obtain, in fact, non-perturbative numerical solution. We did that, it works, it's easy. Or you could construct semi-analytic perturbative solution. And since it's for the purpose of the talk, I'll present the next slide, this perturbative solution. So what you do is you consider a perturbative solution in which you consider a limit in which the number of, in which the radius of the cavity is large compared to the V4. So the meaning of this is that the mass of the hypermultiplet is big compared to the energy scale associated to the 't Hooft coupling. So in this case, in this zero-dimensional case, the 't Hooft coupling is dimensionful, and so it has dimension 3, and then and that's your condition. So essentially, your bare mass is much larger than the energy scale associated to the 't Hooft coupling, and in this limit, you can obtain a perturbative solution. Analytic. Well, analytic modulo this integral. So what you do is you expand perturbatively your function h, and you expand also perturbatively the solution inside the cavity, and matching the solutions inside and outside the cavity order by order, you can obtain your perturbative solution. In fact, in our paper, which, well, hopefully will be published these days, we have a more general approach, formal approach that gives, to all orders the perturbative solution, but in practice, you can only solve it in closed form up to first order. Beyond first order, you cannot do it in closed form. And even here, well, that's not exactly closed form, but you can imagine that this is some nice special function, and then it is. Okay, so this is what I wanted to share with you today. Thank you for your attention.
Is there any question from the audience? No. And also from remote, there is none. So if not, let's thank the speaker again. And pass to the next speaker, who is Kristina Giesel. You are there, I can see you. So you are free to start. We still don't see your slides.
Yeah, I'm just starting to share. Can you hear me?
Yes.
Okay, perfect.
Now we see also the slides.
Okay, so first of all, I would like to thank the organizers that they give me the opportunity to speak at this workshop. And I will talk about a reduced phase-space quantization in loop quantum gravity and how this can be applied to the setup of loop quantum cosmology. And I will discuss loop quantum gravity in the canonical framework. And therefore, we have to find a strategy how to deal with the constraints which we have in canonical general relativity. And there are basically two approaches that one can follow. One is Dirac quantization, where you first quantize your theory at the kinematical level, and then you want to solve the constraints in the quantum theory. And if you perform this step, you basically get as an intermediate step a so-called kinematical Hilbert space. And on this Hilbert space, you implement the constraints as operators, and then you require that physical states of your theory are annihilated by these constraint operators. And then there's a second approach, which is called reduced phase-based quantization, which rather take the opposite approach. And you try to solve the constraints already at the classical level, which brings you into the physical phase space. And then you quantize only the physical phase space. And this allows, after quantization, to get a direct access to the physical Hilbert space. And on these physical Hilbert space, we are interested in the dynamics, which is encoded in a so-called physical Hamiltonian, which is like in ordinary theories without constraints, a true Hamiltonian that is not vanishing on the constrained hypersurface. There are two things where both approaches can become complicated. For the Dirac quantization, it basically is the step where you try to find solution of these operator valued constraint equations. And if you follow reduced phase-based quantization, then it can happen that the algebra of your observables at the classical level becomes complicated, and then it might be hard to find the corresponding representations which give you access to the physical Hilbert space. And in practice, basically, not one approach is favored over the other. Often you just combine the two approaches and you solve some constraints by Dirac quantization and some by reduced quantization. So if we follow reduced quantization, what are the steps that we have to do? The first one is we need the algebra of observables, and this means at least for part of the constraints, we need to solve them at the classical level, and then get a partially reduced phase space on which we can implement this observable algebra. And in a second step, if we aim at quantizing this theory, we need to find representations of this observable algebra. And one requirement which we use here is that we only want those representations which support the dynamics, which means that we are only interested in those where we can also implement these physical Hamiltonian as an operator. So the question, if we would like to follow reduced phase-based quantization, is what kind of choice, or if we choose one kind of observable algebra, how does this influence the final quantum model? If we go back to GR and formulate this in terms of Ashtekar variables, which is the starting point for loop quantum gravity, then the gravitational part is parameterized by the Ashtekar connection denoted by A here, and the corresponding conjugate triad, capital E. And full Dirac observables would satisfy that they Poisson commute with all constraints, which are the Hamiltonian C, the diffeomorphism constraint C vector. And in the case of Ashtekar variables, we have an additional Gauss constraint. Now, the models I will talk about here in this talk, they have a partially reduction with respect to the Hamiltonian or the Hamiltonian and diffeomorphism constraint, but the Gauss constraint is solved at the quantum level via Dirac quantization. Now, if we want to construct these reduced observables, we use the so-called relational formalism. And the main idea of this formalism is that you couple additional fields to general relativity or the system that you are interested in. And by means of these additional fields, you have a way to construct these Dirac observables. And the strategy is the following. For each constraint that we would like to reduce at the classical level, which I call Ci, so I is some index, we introduce some additional reference field. And this additional reference field is dynamically coupled to general relativity or general relativity plus some other matter, and then really serves as a dynamically coupled observer with respect to which we formulate the dynamics of the remaining degrees of freedom at the gauge invariant level. And one consequence, of course, if we couple additional fields to general relativity is that we get additional contributions in our constraints, and therefore we have some contribution coming from gravity, which I called geometric here, and then some additional contribution in each constraint, which come from the reference fields. the idea how we can solve or construct observables in this relational formalism is that we consider these total constraints, including gravity plus our reference field, and then we solve the set or a subset of the constraints for the conjugate momenta of this reference field, which are denoted by pi here. The advantage is that this constraint algebra then becomes abelian, and this helps a lot to simplify the construction of the observables. Now, in principle, if we work in this relational formalism, there's no restriction on what kind of reference matter we can choose. But we want to use this formalism to quantize later on general relativity. And therefore, we would like to make our life as simple as possible, and therefore have additional requirements for the reference matter that we consider in these models. One requirement is that this physical Hamiltonian, which is encoding the dynamics, which I was mentioning at the beginning, should be time independent. And this can be carried over to the condition that if we rewrite the Hamiltonian constraint, which I denoted as C naught twiddle here, a linear in the conjugate momentum to the temporal reference field denoted by P naught, plus some phase-space dependent function, which in general can depend on the gravitational degrees of freedom A and E, but also on the temporal reference field T naught. Now we are only looking at models where H naught either depends only on the gravitational degrees of freedom, or it can still depend on the reference field T naught, but only via its partial derivatives. And then this is sufficient to get a finite physical physical Hamiltonian, which is time independent. The second step is to construct the algebra of these observables. And also here, of course, we could choose any reference matter. We could even choose geometric degrees of freedom to do that. But here we would like to have the algebra of observables as simple as possible, and in the best case, just to satisfy standard Poisson bracket relations. And this allows them to carry over quantization techniques that we have also used in the Dirac quantization approach to the reduced case. Now the question comes, which reference matter satisfies these kind of criteria and which should we choose? And there has been a lot of work in the literature already. And all this work has chosen dust models or scalar field models. And I will also restrict the discussion in my talk on either dust or scalar field models. So the dust models that are available in the literature can be parameterized by one Lagrangian density. And this Lagrangian density includes up to 8 scalar fields which are encoded in Ti. I runs from 0 to 3, rho Wj, where j runs from 1 to 3. And then some arbitrary functions, alpha, beta, and lambda, which depend on rho. And then this function v mu, which includes covariant derivative of the Tj field contracted with the Wj fields. And then depending on the choice of alpha, beta, and lambda, you can basically get the existing dust models that are available in the literature. So for instance, if we choose alpha, beta, lambda equal to rho, we get the time-like dust model from Brown and Kurkcuoglu. If we choose different values, we can also get null dust, non-rotational dust, and Gaussian dust. And these are all models which have been looked at the classical level or the quantum level by Kurkcuoglu and his collaborators. Now, if we perform a canonical analysis of these models, we distinguish 2 cases. One case is where alpha and beta are non-vanishing, which means we have these additional second and third term in the Lagrangian density, or the case where these 2 vanish. And in both cases, it turns out that the system you have to deal with becomes second class. Now, the second class constraint can be solved strongly, and then this means that the fields rho and Wj can be expressed in terms of the remaining fields. The difference between case 1 and 2 is that in the first case, you obtain a first class system with 4 additional scalar fields, T0 and Tj, so these dust fields. And in the second case, you just end up with 1 additional dust field, T0. So in the first case, you could reduce the Hamiltonian and diffeomorphism constraint, but in the second case, only 1 constraint, and usually you choose this to be the Hamiltonian one. Now let's look at this H0 function, which we had in the rewritten version of the Hamiltonian constraint. And for these models I was just mentioning, in time like dust, this becomes a function which automatically only depends on the gravitational degrees of freedom. And in all other models, this still depends on the temporal reference field T0, but only via its spatial derivative. And there, this was something we were fine with. In the second case, we have a combination of the spatial derivatives of the temporal reference field contracted with the inverse ADM metric. And this basically can be also replaced by the diffeomorphism constraint. We usually call this the Brown-Kukash mechanism, and then you end up with a weakly equivalent expression of H0, which also only depend on the gravitational degrees of freedom. Now, the second type of fields that were considered are scalar fields, and the most simple model you can think of is a massless Klein-Gordon scalar field, where you just have the Lagrangian density shown here on the top, and T0 is again a temporal reference field, which usually is used for the Hamiltonian constraint. Then people have also looked at more generic Lagrangian densities with one scalar field, where you allow the Lagrangian density to be a function of this typical kinetic term capital I. In order to also have scalar fields which allow a reduction not only for the Hamiltonian constraint, but also with respect to the diffeomorphism constraint, people also introduced scalar field models with more than 4 scalar fields. And there's one with 7 additional scalar fields encoded in this MJJ here on the bottom of the slide. And then you have a second class system. If you reduce the second class constraint, you end up with a first class model, which includes 4 additional scalar fields, chi0 and chi-j. So let me say a few words about the dynamics at the classical level. So we can construct observables in all these models. And as reference fields, we choose one of the fields that we additionally couple to general relativity. And then we can also construct these physical Hamiltonian, which becomes the Dirac observable of these lowercase h0 function, which was the additional term in the Hamiltonian constraint rewritten in a form linearly in the clock momentum. So, and for the dust models and for the one scalar field models, I have just written down the Hamiltonian densities here below. So you see, for instance, for the time-like dust model, we have a square root Hamiltonian, which includes the square of CGO, which is the geometric contribution of the Hamiltonian constraint, minus a square of the diffeomorphism contribution of geometry contracted with the inverse metric. And then we integrate over all spatial physical coordinates to get the physical Hamiltonian, as seen on the top left box here. And if you look at the different dust models, for instance, non-rotational and Gaussian dust, they have Hamiltonian densities which include no square root. And if we consider the one scalar field model for a massless scalar field, you basically end up with these double square root Hamiltonian density. So what we realize is the form of the physical Hamiltonian depends on the choice of reference fields we choose, which is not too surprising because we use one of the reference fields as a temporal reference field. So now the main question of my talk is the following. If we apply such a reduced phase-space quantization in loop quantum gravity, then we add some additional scalar fields, which means we add some additional matter input. And this allows us via the relational formalism to access the physical Hilbert space. And of course, we can choose different reference matter. And in principle, we expect that for different reference matter, we get different models. And then if we quantize, there might be different features of these quantum models. In particular, because we dynamically couple these reference fields, and therefore we expect already at the classical level that we have some back reaction of these reference fields, and therefore they might have an influence on the quantum model as well. So therefore, the main question of this talk is, what is the physical imprint of chosen reference matter? Now, if I stay in the framework of full loop quantum gravity, what I would need to look at are the full quantum Einstein equations, which include the operator version of these physical Hamiltonians, which one can write down in all the models I was discussing before. But you can imagine these are quite complicated at the level of full loop quantum gravity. Therefore, the strategy of the work I'm presenting here today is to use a simplified setup and to analyze this question in the context of loop quantum cosmology. In loop quantum cosmology, as a first step, we consider effective techniques in order to analyze what kind of effects we can have from choosing different clocks. So we take the reduced phase space of general relativity as a starting point, and we want to do cosmology. So we are not considering only gravity plus our reference matter, but we also would like to include an inflaton and then also analyze whether these different choices of clocks have some influence on the occurrence of inflation. Therefore, we consider the action which is given by the standard gravity action plus an inflaton action and then some reference matter. And in our work, we analyzed 3 different reference models: Gaussian dust, Brown-Kukash dust, which is the time-like dust I was mentioning before, and then the 4 scalar field model. And as I mentioned already, why we are choosing these kind of reference fields or reference matter is really guided by the choice of simplicity for the final resulting quantum theory. Now, the first step is to construct these Dirac observables. We can do this in the dust models and also in the scalar field models. And I won't go into the details how you actually construct these Dirac observables, but roughly speaking, it's a combination of your variable that you would like to make gauge invariant, for instance, the Stecker connection, and then powers of the reference fields that you consider, weighted by terms which include the Poisson bracket between the constraint and, in this case, the Stecker connection. You do this for all elementary phase space variables, and I denoted these Dirac observables here by OA, OE, and we do the same in the inflaton sector and then get a Dirac observable U phi and OP phi. So the additional label capital T here refers to the fact that these are observables in dust models and the temporal reference field is capital T. And when we consider the scalar field model, we have as a temporal reference field chi-0, and therefore we have a different temporal reference field label in the second line. One can show that the algebra of Dirac observables indeed satisfies for all elementary variables the standard Poisson brackets, so quantization in the usual manner is no problem here. Then we can write down these physical Hamiltonians for the Gaussian, Brown-Kukash, and scalar field model. And I have shown below here again the Brown-Kukash, so the time-like dust model with 1 square root, and the 4 scalar field model with these double square root included. So now we go to loop quantum cosmology. And as usual, what we do is we do a cosmological symmetry reduction before quantization. So we symmetry reduce to the FLRW sector for k equal to 0, and then quantize this theory. And we consider these 3 different models. And if we go back to their physical Hamiltonian, we know that in cosmology, the diffuse trivially vanishes. Therefore, of course, these physical Hamiltonians will simplify, and also some square roots will be gone. Now, if you compare to already existing models in loop quantum cosmology, like for instance, the APS model via Stecker, Pawlowski, and Singh, then the difference to the models we consider here is that because we couple in addition the reference matter, either dust or a scalar field, we consider 2 fluid models, because we also have these inflaton in addition. In the APS model, you just have the inflaton, which you use as the clock. So the downside is that we have to deal with a more complicated system because we have 2 fluid models. However, the plus in these models is that if we don't use the inflaton as a clock, we have no problem to add arbitrary potentials to the theory without having the effect that the physical Hamiltonian becomes time dependent, which would be the case in the APS model. Now we use the elementary phase space variables for loop quantum cosmology, which are the volume and the conjugate variable, which is the corresponding connection, and some scaled by some power of the volume. Then we have the inflaton, degree of freedom, and its momentum. In this simplified setup, they satisfy the standard Poisson brackets. And if we look at the physical Hamiltonians in the cosmological sector, as I said, for the Brown-Kukash model, the square root is absent. And in the scalar field case, we just have one instead of two scalar fields. And the potential of the scalar field here, we just denoted by U. So now we perform a quantization. Since this is formulated in terms of Dirac observables, we can access directly the physical Hilbert space of the theory. We don't have to go via the kinematical Hilbert space, and this consists of a tensor product of the gravitational part, which we quantize as usually in loop quantum cosmology using the Bohr compactification of the real line, with the corresponding inner product just shown here in the third line on the right. And then the second Hilbert space in this tensor product is the one for the inflaton, where we use the standard Schrödinger quantization. Now we work in the volume representation, which means that the corresponding operator to the volume acts diagonal, shown here on the last line in the left. And then the second elementary operator is associated to the holonomy, and this just shifts this new label of our states by one. We can perform the same exercise for the scalar field model. Also there we have two parts in the tensor product, gravitational and inflaton. And the only tiny difference is that we slightly changed this Bohr measure by a factor B, depending on the volume here. And this is just due to the fact that we want to make sure that our physical Hamiltonian is a self-adjoint operator in this theory. But we also work here on the volume representation, so the operators act similarly. The quantum dynamics in these models is given by a Schrödinger-like equation. This is also true for full loop quantum gravity. So on the left-hand side, we have a temporal derivative with respect either to dust time or scalar field time, denoted by tau and tau chi here. Our states depend on the configuration variable of the gravitational part, the volume, and then the O phi of the inflaton, and then of course on the temporal coordinates. So in the second line, there should be a tau chi. It's a typo, sorry. On the right-hand side, we have the Hamiltonian, which is here really a true Hamiltonian. It's not vanishing on the constrained hypersurface. And we see again, as expected in the scalar field model, we still have the square root and some multiplication by volume terms. And in the dust model, we just have the two contributions coming from gravity and the inflaton. Now we quantize those operators using standard LQC techniques. We choose the same operator ordering like in the APS model, and shown below here, you find the explicit form of the quantum operators, and the sine and cosine terms here just come from expressing the B variable in terms of the corresponding exponentials. So this is the full quantum dynamics that one can formulate in these reduced models. And let me mention again, also here we see we don't have any restriction on choosing the potential of the inflaton U because it's not a temporal reference field here, so our Hamiltonian will be time independent. Now in our analysis, we didn't analyze the full quantum dynamics yet, but we went to the effective level. And this means that we can write down an effective Hamiltonian for these models. So let me start with the dust model, which mimics well these quantum geometry effects. And if we write down these effective Hamiltonian in the dust model, it has this form here, and we see still some imprint of the polymerization in this sine squared term here. Given this effective Hamiltonian, we can derive the equations of motion for our elementary variables like volume, like the conjugate variable and the inflaton and its momentum. And this is basically describing effectively our dynamics. From this, we can derive a modified Friedmann equation, which has the usual form. So we get the same result as in the one fluid models, with the difference that the energy density on the right-hand side, which enters, now basically consists, of course, of the contribution from the inflaton and the dust reference field. And we get the same correction here on the right-hand side, which is causing the bounce we usually have in these loop quantum gravity models. Now we do the same for the scalar field model. We quantize also here the Hamiltonian and then derive the effective Hamiltonian, which still includes the square root. We can derive the corresponding equation of motions and also get from it a modified Friedmann equation shown below. I put an H-twiddle here on the Hubble parameter just to emphasize that this is now dynamics with respect to the scalar field time tau x. And also here we have the same form and also the O rho, so the observable associated to the total energy density will include contributions from the scalar field clock. Now let's look at a more detailed analysis, and the question we wanted to ask is, in this effective setup, how does the choice of clocks affect inflation? For this, we had to choose a particular potential, and here we chose a Sarobinsky potential with its mass value. And sorry.
Okay. So then we can continue because the next speaker is not ready yet. So okay, go on.
Okay. Just let me share. So we chose initial conditions at the bounds, which is at pi over 2 lambda here, and then we choose an initial Planck value at the bounds of 1000 Planck units. We can parameterize the initial conditions by choosing the value of the inflaton and its momentum, but this determines our energy, so the effective physical Hamiltonian, and this is related to the clock energy density, so we can also parameterize initial conditions by the value of the inflaton and the energy density of the clock. Here we choose some initial conditions shown below of the plot, which are guided also by what one has looked at in loop quantum cosmology for one fluid models. And we see these typical bounds here at tau equal to 0. So we get a contraction of the volume, then the bounce, and then it re-expands again. We looked at the point when inflation happens here on the right-hand side in the plot, and we see that the onset of inflation is roughly at 3 times 10 to the 5, and the end of inflation is in the dust models by roughly 5.46 times 10 to the 7th. Now we also checked the first slow roll parameter, and indeed it reaches the value 1, it decreases and then reaches 1 again. So we are sure that this is really a slow roll inflation. And then we compared the kinetic energy and the potential energy to the dust energy density. And we see that the dust plays a subdominant role from the bounce until the end of inflation. And this is also what we would like to have, because this dust serves as a reference field, so we don't want it to dominate the system. So we were looking for initial conditions where this indeed happens. Another criteria is that we wanted initial condition such that the number of E-foldings doesn't contradict experiment. And we see for the dust models, we get 63.1, which is slightly lower than the LQC result where you have no dust, which is 63.9. Then we looked at the number of E-foldings in the case where we increase the dust energy density. So we keep the value of the inflaton field at the same initial value, and then basically vary the dust energy density from 5 times 10 to the minus 8 up to 10 to the minus 4. And what we observe is that the number of E-foldings is decreasing, and we think this happens because we have a larger Hubble friction when the dust energy density is increased. Then we can ask the question, how large can we make this dust energy density until inflation does no longer occur? And for the initial condition we choose for the inflaton field, this happens in this model at roughly 1 times 10 to the minus 4. We did the same in the scalar field model. You see here the volume plotted against the scalar field time, and in order to be better able to compare to the former results, we plot the coming up results also with respect to dust time. And you see that inflation starts roughly at the same points, but it lasts a little bit longer compared to the dust model. Here also we checked the slow roll parameter, and also here we could confirm that it reaches 1, decreases, and reaches 1 again. And then we did the same analysis as we did in the dust model, namely we looked at the number of e-foldings and how they change if we increase the clock energy density. And what we see that if we increase the energy density of the scalar field clock, the number of e-foldings is less sensitive to it. So only if we increase the clock to 10 to the minus 3 Planck units, the energy density, then we see a significant drop, which also means that the influence of the scalar field clock is less significant than the dust clock. This also is reflected in the fact that we have more or less nearly the same number of e-foldings as if we compare them to the loop quantum cosmology one fluid model. And this brings me already to the end of my talk. So the talk basically consisted of 2 parts. The first one was a brief review on a reduced phase-space quantization for loop quantum gravity, where I focused on the different reference meta models that were used in the literature so far. And then I moved to the second part, where we considered a reduced phase-space quantization for loop quantum cosmology using 2 different reference fields, which I also called clocks because it's a temporal reference field, namely one dust field or one scalar field clock. And as a first step of this analysis, we considered effective techniques to analyze the equations of motion. The analysis shows that there exist initial conditions such that we can choose these 2 kind of reference models as clocks, and they have no significant effect on the dynamics. And both models show a qualitatively similar behavior and can serve in this sense as good clocks. There are slight differences. So the scalar field model has a larger number of e-foldings, and also because the number of e-foldings is less sensitive to increasing the scalar field energy density, it can also serve as a clock model in a larger parameter space. Future steps are now to investigate the full quantum dynamics in these cosmological models, and this will also give us the opportunity to double check the effective techniques for 2 fluid models, which we have applied here. So thank you very much for your attention.
Any questions from the audience? Dele, please. Yeah. Yeah.
Hi.
It's a question that I should have asked perhaps several years ago when I started to listen to these things, but it came during your talk. So this is a quantization, but I don't see where is H bar. Because
Okay.
I can see clearly the scale of G, the Planck scale, or I don't know, but the gravitational scale. But I don't see H bar where it's hidden.
Okay, so if we quantize in full loop quantum gravity, you're completely right. As the coupling for general relativity, we have G. But then this is at the level of Poisson brackets. So if you basically quantize, you replace Poisson brackets by 1 over H bar times commutators, and then you combine H bar with G together as the Planck lengths. So now if we look at these cosmological models, let me just find the slide where, so for instance, here this lambda. Lambda, I said, is basically the square root of delta. And delta is a polarization parameter, which is proportional to the Planck length, which again includes H bar.
Okay, thank you.
So what is usually H bar is always the Planck length in our case. That's also why, for instance, the volume operator and so on has certain powers of the Planck length, which then includes H bar.
Yeah, other questions? No, and also from the... Yeah. No remote question. Okay, let's thank the speaker again.
I'm Fedele, I'm not the chairman, but because I was in contact with people. The next speaker has communicated that he's not coming. I wrote to the speaker after that, so the next speaker was Bhattacharya. The speaker after that, Joanna, is, I wrote to her, but she answered that she's in, it's early Saturday morning for her. So she's going to the office she's going to the office. She wrote to me at 6, well, about 20 minutes ago. And I think we should wait for her because she's running we cannot start without her, but yes, because of course, we put her as in the program as a last speaker because she's in the west coast of the US. So we put her, but then we had this unforeseen fact that the speaker before has canceled. So I think, I don't know if Kristina was to say something else or whoever. I'm sure she'll be on time for her talk, which is in 15 minutes. Perhaps we can have an extra cup of coffee or. Okay.
Yes, yes. Of course. No need of excuse. Okay. Joanna, are you there? Are you there? Hello? She's connected. Okay. She's there. Hello, Joanna. Hello, Joanna. Are you there? You have been running?
Can you guys hear me? Can you guys hear me?
Yes, we can hear you. Are you ready to start or you want one more minute?
You know, I will be, I think given that I'm going to give the talk on a tablet and my normal plan would have been to have a second camera for the video. So if you don't mind, I'm going to turn the video off because otherwise you'll be looking at my ceiling.
Okay.
So I'm just going to turn the video off and leave the sound on.
Okay.
And now I will share my screen and then I should be good. Assuming, of course, that my...
Yes, now it's visible.
You can see my lecture from yesterday. That is not the correct thing. I'm sorry, I usually do this ahead of time, but I did literally just walk in as
It's very suggestive.
Okay, all right. We're all good.
Okay. Last but not least, speaker of this evening is Karczmarek, Joanna, who will speak about target space entanglement entropy, matrix models, and noncommutative geometry. Please, Joanna, proceed.
Well, thank you. I want to thank the organizers for giving me an opportunity to speak and for well, being, you know, excellent at running a conference at this unusual and singular time. So I want to talk a little bit today about these topics of target space entanglement entropy and how that works out with respect to matrix models and what we can learn if we look at the particular solutions to matrix models that we know to have a non-commutative geometry as an effective description. So I'll start by just sort of pointing out to people who are not familiar maybe with what entanglement entropy buys us, why should we study entanglement entropy in matrix models at all? So there's been lots of progress over the last decade in understanding in ADS CFT that entanglement entropy on the boundary is related to various geometric quantities in the bulk gravitational theory, and particularly to areas of various surfaces through the so-called Ryuta-Kayanagi formula. And this connection has helped us much better understand how in detail space emerges in the holographic picture. But of course, in this holographic ADS CFT picture, we only get one new dimension. So if we start with, let's say, a three-dimensional space in ADS4, sorry, in CFT 4, we end up with one extra dimension in ADS-C in ADS5. So that's already interesting, but in matrix models, we have a hope that we can get an example of a fully emergent space. For example, in the BFSS model, or maybe even a fully emergent space-time in the AKKT model. And we would really like to identify some entropic quantities in the matrix models that could correspond to geometric quantities in the emergent theory. So that's the general plan. And with that plan in mind, I'm going to review a little bit of work by other people that has led me to what I want to say. So target space entropy in general was just very recently discussed by Mazenk and Ranard in a very nice paper where they outlined a fairly ambitious program that they would like to try to get started, with their main motivation being both matrix models and world sheet string theory, both of which have the property that the space that the physics happens in is not the base of the theory, but the target of the theory, meaning it's the fields themselves that live in the space-time, in the gravitating space-time. And so in order to try to understand how to do entanglement entropy in these theories, they started studying how you do entanglement entropy in target space rather than base space. And this has in fact already been nicely reviewed here by Asato Tsuchiya on Wednesday. So I won't repeat exactly what he said. I'll try to say it in a slightly different way to give you maybe a slightly different perspective on it, and then to remind you what was said. So the example that makes this clear and that is quite relevant to us is if I have, let's say, n identical particles that live in some target space, so are able to move through some manifold. And if I have this target space, this is my target space, I will divide the target space into two pieces, into a region A and its complement A bar. And with this division, I will now, the plan is to try to associate with the region A that I am interested in calculating entanglement for, associate with it an algebra of operators that act non-trivially only on those particles that are inside A. So I have a whole bunch of particles, and let's say out of n of them, some subset, let's say K, are in some particular quantum state, can be thought of as being here. Well, it's not even in a quantum state, right? The quantum state contains lots and lots of is a linear combination of states where particles might be different numbers of particles might be split in different ways between those two regions and its complement. But there exists an algebra which there exists an algebra, and that's written down explicitly in this paper. They write an algebra that implies an existence of a decomposition of the Hilbert space into a direct sum of tensor products. So here, this is quite sort of obvious, meaning we have the Hilbert space of the whole theory can be written as a direct sum of different sectors with different split of these particles between A and A bar. So there could be, let's say, there is a sector with no particles in A, a sector of 1 particle, 2 particles, etc., all the way up to the total of N. And then once you're in this sector, you can then write that in that sector, you can that portion of the Hilbert space can be written as a tensor product of a just the physics of the whatever particles you have in A, Hilbert space for that, times whatever particles you have in A bar, the Hilbert space for that, and then you multiply that out, tensor product. So that's what I said here. And this decomposition then allows us to define entanglement entropy associated with A in any quantum state of the system without having a Hilbert space that the Hilbert space itself is a tensor product of 2 smaller Hilbert spaces. It is a sum of tensor products. So this is a more general definition than the usual definition that is given, or the simple definition that is given for entanglement entropy based on just tracing out the degrees of freedom in A bar, because you basically have to trace out those degrees of freedom separately in every sector, depending on how many particles are in that region.
Excuse me. May I ask you if this special algebra, I mean the operators from region A can map outside also into A bar, or I should map a particle in A already still in A?
Yeah, so it's mapping onto, so if I had just as a simple example, if I had one particle, living in some coordinate X, then the algebra would basically be integrate over the area, over the region A, dx bar. So this would be, the algebra would be generated by operators like this. Make it a little bigger so it's easier to read. So this is basically all possible operators acting on the one particle that only really does something non-trivial if the particle is in region A and doesn't do anything if it's outside of that region.
Yeah, but can it map outside A or not?
That's the whole point. The whole, by construction, it does not.
It cannot, okay.
Right, so that's by construction it does not, and it is because it's constructed this way that it then implies the existence of this decomposition into the direct sum of tensor products. And that's a general theorem. Okay, so if we wanted to extend from n particles to a matrix, this could be simple if I have one matrix. So this is just in one matrix example. It's relatively simple because the matrix itself can be diagonalized. So if I have if I have a theory of a single matrix, then we know that we can usually integrate out the off-diagonal degrees of freedom, diagonal, and work just with the eigenvalues of the matrix. And now those eigenvalues will act like particles, whether they are free or interacting depends on the details, and whether we treat them as bosons or fermions. But either way, we can treat them as some kind of particles. And you did see an example exactly of that in Asato Tsuchiya's talk. But of course, models such as BFSS have more than one matrix, and it is, to extend to multiple matrices, becomes much more complicated, and that's where that a lot of the intricacy of emergent geometry is going to live in this in this fact that you have multiple matrices. So the proposal for or the attempt to start thinking about this was in this paper by Das, Kaushal, Mandel, and Trivedi about a year and a half ago. And what they had said is they said, okay, we'll continue to diagonalize one of the matrices and work with that. And we need to diagonalize whatever matrix allows us to simply specify our region A. So the simplest example would be that I have, many directions, each of which is associated with some Hermitian matrix, like in the BFSS model. And I will diagonalize X1, and in some particular, and I will define a particular region by saying that I'm interested in everything to, let's say, the left of this plane. And so I have a plane here. And anything to the left of it for X1 less than 0 is, let's say, my region A. And to the right, I have my A bar. If I want a more complicated geometric region, what you have to do is find a coordinate, which might be a complicated function of the coordinates you have. Find a coordinate whose level set gives you the surface that divides your space into two pieces, and then try to work in a gauge where it is that complicated matrix, which might be a nonlinear function of the original matrices, is diagonal. So one simple example of that is a situation where, let's say you define a matrix let's call it R2, by which I really mean 1R squared, which is the sum of all 9 matrices squared. And if I work in the basis where this is diagonal, then I have a relatively easy way of defining regions which are basically balls in the 9-dimensional space. So the dividing surface is an 8-sphere. And in principle, we could do this for more complicated geometries. So the fact that we have complicated geometries is probably not the hard part here. The hard part here is that the construction does not tell us at all which entries of the non-diagonal matrices, the remaining, let's say, 8 matrices, here X1 through X9, which ones should this algebra include? And that's the question. So that's the question that they argued about here, and the argument is is physical, and I will try to tell you what it is that they have argued. So they basically said, okay, let's think about it like this. We know that, let's say, an IKKT model, you should think of these. We should think of the matrices arising as degrees of freedom of open strings living on a bunch of D-branes. And so there is a picture that I can have, that if I have my region A, to the left of, let's say, this line, and so my region A is on this side, I might have some D-branes. So the particles I was talking about earlier, I can think of as D-branes that live to the left of the line, and then I have more D-branes outside that region to the right of the line in a complement. And I drew them as dots, but in fact, since we were only able to diagonalize one out of the matrices, it's only really their position in the X1 dimension that's well defined, and the other dimensions, I should think of them as fuzzy, which really means I should think of them as fuzzy in all dimensions. But at the moment, I believe I have well-defined X1 coordinates. That's where my algebra, how I'm going to define my algebra. And the matrix, let's say now I consider, let's say, a matrix X2. Let me draw here a big square to represent this matrix. And I can say, well, let's consider, let's say, the first 3 however many I have over here, however many I have in A, there's some number, some number of entries in that matrix. Sorry, I did not mean to say N, I was supposed to say A. There we go, A. So the degrees of freedom inside of this square, we can right there, we can easily interpret as open strings stretching between all these D branes on the left hand side. And I think nobody would argue that when I'm interested in the degrees of freedom living inside of the region A, that those are not relevant. So we keep all the different operators that live in this part of the matrix and make that part of the algebra. That's I think that's definitely inarguably true. We also want to have a whole bunch of, same thing is true for the outside. And I think, again, nobody would argue that any of those open strings should be considered living outside of the region A. Outside of the region A bar. And so those definitely we want to trace over. But then there comes a question of, well, what do we do with open strings that stretch between this way? All the open strings that stretch across the surface, right? So these are these regions here in gray, and we need to decide what to do. Should the operators in that part of the matrix be in the algebra or out of the algebra? And the proposal in these two papers said, well, basically they made two proposals. The Das et al. Made two proposals and said, okay, either you include all of them or you don't include any of them. And then in a follow-up, in a similar paper, Hampapura, Harper, and Lawrence argued to include just one of the regions. And by the way, this collaboration had one more paper describing this in a more gauge invariant way, rather than picking a gauge with the matrix as diagonal. So in both cases, the argument was, well, we have to do something with these strings. And if you sort of take a majority vote, it seems that the way that they would be leaning is to say, okay, we're not going to include these strings, these gray strings, as being part of the region A because they're not fully there. We don't know everything about them. So let's just trace them out. And I have an issue with that. And my main issue with that is that if we do that, of course, if we do that, then when we calculate the entanglement entropy for A, we don't include the gray strings. But when we try to calculate entanglement entropy for A bar, we also don't include the gray strings. And we know that when we do that, we're not going to get this nice property that when the system is in a pure state, the entanglement entropy of a region is equal to the entanglement entropy of its complement, which to me, it seems like we are basically treating, just because we've divided the region of space into two pieces, we've basically assumed that there are some degrees of freedom that cannot be, that the system basically acts as if it wasn't in a pure state. And I'm not sure that that's the right way to go about it. And so what I wanted to think about is that, well, there is a place where this becomes a lot easier to study, and that's where instead of these all these things being, let's say, in some quantum state in which they have a very complicated wave function, such as let's say the ground state of the IKKT model, where we don't even really know what the wave function is yet. That it would be easier to study this if we had a matrix model which has a classical solution with some nice geometric interpretation for the configuration of those D branes, let's say, that has a nice non-commutative geometry interpretation. And so the let's say if I again I go to a gauge where one of the matrices is diagonal, and I can choose one of these matrices to be diagonal, that those eigenvalues now will have a well-defined classical distribution. So instead of having to worry about, well, you know, I have sectors where I have one eigenvalue to the left and two eigenvalues and three eigenvalues, etc., I might actually be able to sort of say, on average, classically, there is a certain proportion of all the eigenvalues live in the region and certain proportion live outside of the region. And so the example here is the very simplest example possible, which is if you take any matrix model that happens to have a non-commutative sphere, as its solution, and just to remind you, though I'm not sure this audience needs a reminder, the non-commutative sphere solution is one where let's say we have three matrices that are non-zero in the classical solution, and they are proportional to the representation matrices of SU2 in some irreducible representation. And then when we have that, any fields that live on this sphere, well, any effective fields in this picture and the fluctuations around this classical solution are represented as fields. Also gauge fields, it's a little complicated, but the simplest thing you can have is a scalar field, and in a free limit, the scalar field is represented by the following Hamiltonian. So that's the limit in which I want to work. And I will take the matrix in the X3 direction, as usual we do, to be diagonal. So I'm taking L3 over here to be diagonal. And we've studied the entanglement entropy in the setup in quite a lot of detail in a series of papers. Some of the HepTH numbers are here. And Hongzhe Chen and Charles Rabideau and Philippe Sabella-Garnier were my students. And some of them have written papers on this on their own as well. So what we have learned is that we can quite easily define here which of the entries of this scalar field matrix should be thought of as living inside or outside a particular type of region. So the regions we were using are spherical caps, so we can take advantage of the remaining azimuthal symmetry. And we've argued in various ways, but how to do this, but the simplest and I think really deepest way of defining the correspondence of the geometric region up to the portion of the matrix is that consider an operator. So here I say Z instead of X3. Consider the operator. Consider an operator which is basically trying to measure the height on the sphere. So if I take my field, I can multiply it in a symmetric way by the L3 matrix. And if any fields that have eigenvalues larger than some cutoff that is easy to determine here can be thought of as being inside, and any fields that have smaller eigenvalues can be thought of as being outside the cap. And you know, a tiny little bit of thinking about how this works tells you that you should associate the inside of the cap with this triangular region. And so if I were to ask, well, where are the D-branes in some sense? Well, if I diagonalize the Z3 matrix, then my picture should be that that's an equally spaced spectrum, and my sphere is there because the matrices, the other two matrices kind of smudge over the sphere this way. And so I am going to, so if I want to put D-brain dots for the D-brains, I will have to put them, let's say, on these circles. Hope this is clear. And what this says is that you will want to take not just the not only do you include the degrees of freedom whose both ends are inside the region, both the ends of the open string are inside the region, but also somehow half of this other disputed region. And so you might say, well, does this make any sense? And it turns out that in this picture of non-commutative geometry, the resulting entanglement entropy behaves very well. It reproduces all sorts of holographically predicted behavior for n equals to 4 non-commutative super Young mills. So this was one of the right, we had studied the non-commutative Young mills in the holographic picture and discovered that there's a certain phase transition that happens that I don't think I'm going to have time to describe in great detail, but we were able to reproduce that phase transition by imposing a UV cutoff in the matrix model in a way that's similar that it is imposed in the holographic picture. We also get a perfectly finite and reasonable mutual information that reproduces the commutative result. How much time do I have left? Sorry?
It's over, but you can have a little more.
Okay, about five minutes. That's fine. So I have here a bunch of slides describing some of these results that I don't really intend to go over in any detail. So maybe I'll pick. Let me pick this one. So there's a phase transition in this entanglement entropy that occurs because if we think about non-commutative geometry as having some length scale, that length scale isn't actually the length scale of non-locality because the actual non-locality depends also on the cutoff, and the effective non-locality scale is, can be very large if your UV cutoff is very small. UV cutoff length scale is very small. That's called the UV-IR connection. And so the way to think about this is that, well, I've got those individual cells, and those are sized with there's 1 degree of freedom, so to speak, per cell. Those are sized with my UV cutoff. I have a non-commutative geometry length scale, which is the sort of the accuracy with which I can define the boundary. And there's a much larger length scale for the non-locality, which allows there to be entanglement between degrees of freedom that are not lying just across the boundary from each other. And that means that when I have regions that whose size is much greater than this red arrow non-locality scale, the theory will start to look roughly local, and we will get area law behavior, which is the standard behavior in local commutative field theories. But when the region is smaller or on the order of this non-locality scale, which is much bigger than the non-commutativity scale, there will be some other kind of behavior. In fact, we could predict that entanglement entropy would be extensive. And this is what we see holographically, and this is also what we see in the matrix model. We can see here, this is a different UV cutoffs. So when I have a, let's pick, let's say the green line here, this is at some value of the UV cutoff. And you can see that the data starts out traveling along the top of this line, and then at some particular length scale, transitions to the smooth line here, and this green line is what you would expect from a commutative theory. So we have a transition from a non-commutative behavior. This is right. This is entanglement entropy. Transition from a non-commutative behavior to commutative behavior. And so this definition of entanglement entropy using this triangular definition is extremely sensible and always has given us very reasonable results, including exactly this mutual information. You can see here, all these plots are right on top of each other, and the plots in this plot include not only different UV cutoffs on the non-commutative sphere itself, but also the commutative sphere result, a discretized commutative sphere, just putting a lattice on a sphere. And it all agrees with, a little bit of jiggle due to some, basically the discretization of the sphere. So using this approach, we can argue that those off-diagonal entries should be split between the region A and its complement. And you're not going to get that very nice triangular picture that I described is really there because the eigenvalues of the X3 matrix, so you might get, for example, a split like this, the shape of this line here is caused because the eigenvalues of the X matrix were equally spaced. When they are not, you're going to get some more complicated shape here, but you should still get a portion of the eigenvalues living, of the entries living inside the region and a portion living outside. And this has a very nice geometric interpretation, which is that if you think about what I wrote down, I have written down one that I said that I'm going to have a map from my field to this, and this is measuring the position. This is the measurement operator, if you will, on that non-commutative sphere for the height on the sphere along the third dimension. Because when I multiply it on the left, if I have an open string that's stretching between two d-branes, the multiplication on the left will return the position of the X3 position of the left, or one of the two ends, and this multiplication on the right will return the X3 position on the right, or on ends 1 and 2, and then I take an average, and in the matrix model where the strings basically are not curved like I drew over here, but in fact straight, this average between X3 left and X3 right this average is in fact exactly the center of the string. And so what I'm saying is that you should include those degrees of freedom whose middles lie inside your region and exclude those whose middles lie outside the region. And so what we need to do is look here, where is the middle of this gray string? And then assign its inside versus outside degrees of freedom based on that. And when we do that, it turns out that we're actually reproducing a picture that has already been used to great effect in the full string theory when people try to calculate entanglement entropy using string field theory. And it is that middle point prescription that has been used there to get sensible results. So that seems to jive with that. And I think I'm going to just leave it at that point.
Okay. You have already spoken 35 minutes. Have you? Can you conclude?
Yeah, I think I'm just going to stop here.
Okay. Thank you very much. Are there questions from the audience? So.
Yeah, this is the elliptic. More than a question, it's possibly a suggestion, although probably useless because the sphere is good enough. But if you, instead of using the fuzzy sphere, were to use fuzzy disk, which is basically a non-commutative plane with a projector, and then the non-commutativity of the plane, which is the inverse of the projector, then it's very easy to get the equivalent of your cap, because if you take another projector, a smaller projector, this one selects the area around the center in a very clean way, and you can do these things. But probably relevant because what you wanted to show, it's already shown with the sphere, but the disk probably would be cleaner. You wouldn't have this problem of this little corner that you were showing, probably, and I haven't looked at it. So just a comment more than a question.
Okay, that's interesting. Thank you for that. It'll be. I have not looked at the disk. I think it'll be interesting to test this on other geometries. The limit is really sort of numerical. The sphere has and the disk would have the same symmetry, but the sphere has that cylindrical symmetry, which means we don't have we can do this. We can break it into different angular momentum around that axis and calculate entanglement entropy for each of these individually, which is how we were able to push these calculations, to such a high n. If we didn't have that symmetry, I wouldn't be able to deal with such large symmetries. But the disk will have the same symmetry.
It has the same symmetry, exactly the same way. It's the commutator with one of the. It's a commutator. No, here it's always a commutator. Yes. But you made your point already. It was just a. Probably it won't take you even long to check of it. But since I did the disk, it's the disk.
Sounds like a fun project for an undergrad.
But that's all. Thank you.
I might find an undergrad to do it.
Okay. Any other question? I think there is one online.
Yes. Yes.
Hello, can you hear me?
Yes, I can hear you.
This is Masanori Hanada speaking from England. Thank you for a nice talk. And it's just one comment that probably if we start the discussion, it becomes long. So it would be nice if we can exchange email and discuss later. But my comment is, you mentioned work by Kentucky and Tatar people, and mentioned they diagonalize X1, but then X2, X3, they cannot be diagonalized, and the geometric interpretation is unclear. Actually, including myself, everybody had the misunderstanding for a long time, and people thought that way. But actually, we can define a simultaneous eigenvalue. But so that was my talk on Wednesday, and I will send you reference and the link later. But
well, I have since all the talks were happening in the middle of the night for me, I have not watched all of them yet.
Yeah.
So please do send me an email, but I'll also make sure to watch your talk.
Yeah, and I think by using, combining my story and theirs, probably the way you treated the fuzzy sphere and the way they wanted to treat the matrix model, they can be more or less the same, I think. So I think we can connect to different approaches. That was my comment.
That would be great. Thank you.
Okay. So it seems there is nothing more. So let's thank the speaker again, and let's see you again tomorrow morning. We start at 9:10 apparently. Yes. Okay. Bye. Good evening.
Thank you.